So good afternoon, everyone. Welcome back from the break. My name is Kaylah McGowan. I just recently graduated from the University of Arizona. I majored in applied physics. I'm the first woman to graduate with that degree from there. Yeah. Thank you. And today I'm excited to talk about my summer research project with ACT CMD data. So, just a clicker. Okay, so I want to start by talking about the cosmic microwave background. You guys may be familiar with the earlier presentations. The cosmic microwave background is basically just the light signature from the early universe. It carries lots of information, including information about galaxies and anything the light encounters that it passes through. Also, it provides measurements on constraints, you could say, cosmological parameters regarding dark matter, dark energy, neutrino masses, etc. And the map that I have here is an ACT CMB map. So without ACT, we would not have this data. And the goal of the ACT telescope is to improve the measurement of these parameters that we have of the early universe, which will lead to testing of models for like inflationary periods, the Big Bang, etc. So there's still debate on whether the Big Bang was a singular event or are there multiple contractions in the universe. We also have the ability to measure distant and large galaxy clusters, like the work that Morgan was doing. And it will eventually help us understand how these structures in the galaxy evolve. The universe. So the goal of our project was to characterize noise in different patches of this sky or different patches of the CMB map. And we have correlated noise that we have to account for. We have point sources, we have sky noise, we have instrumental noise. So you really have to take into account this noise, so you can have more accurate data for spectra and different things. And I also want to note that the CMB map making process is a huge data challenge. It's a lot of data. It requires big computing processing, and as it says here, it's about a terabyte of data that we compress down. And even with these compressed maps, it's still very hard to run the code on them. So here are the types of noise, just some more specifically. We have white noise, which comes from astronomical sources. And we have atmospheric noise, which also is basically our pink noise in this case, which has to do with perturbations in the atmosphere, changes in temperature. It also changes in the water is very important, especially when you're observing in millimeter wavelengths or very long wavelengths. So here is what I did. I created an AutoPower Spectra, and here are some of the steps that I went through. So the first step is we start out with a large map. This is actually a cut of the large map, but we start out with a large map, and we cut this map into smaller patches. So what I have in step 2 is one patch of the sky. And then in step 2, we read in this map patch. We have a beam in the sky that we use, and we normalize that. The beam in the sky represents basically the telescope's viewing window. A larger telescope equates to a smaller beam, which and then is more accurate in looking at smaller features. So in step 3, we then read in our point source mask, which is basically a map of other things in the sky that we want to take out or maybe use, depending on what you want to do with it. We define the shape of this mask and apodize it, which means we are like essentially rolling the edges off to 0 or a number very close to 0. So it's just like a transition, because when we do these Fourier transforms on our maps and data, you don't want to have anything with sharp edges or anything like that. So after we apodize our point source mask, we create a footprint mask, which I did with doing like an array of ones. It's basically just doing the same thing as like we want to have a map that has that apodization that you can see along the edges. And we combine all of these together. An important part to note is in the footprint mask, like areas of the sky where it is red means that we have more data essentially on that. So next we have the coad inverse variance map, and we do the same thing, define its shape, but we don't have to apodize this. And then we multiply all of those together, the footprint, the point source mask, and the IVAR maps to build this final mask, which includes everything. So after that, we calculate the mode coupling matrix and the power spectra. And then from that, we calculate the mean standard error and the mean power spectra for plotting, with a few steps in between, such as binning and things like that to get the data into the graph. And so you can see here, well, this is just one. This is from one patch of the sky, and I have the power spectra plotted with the theoretical power spectra for our galaxy or the universe. And so yeah, let's move on. And here's just a short timeline of our project and the things that I went through: reading in the map, selecting the path of match of sky, and then creating the spectra for each. And then here I have a map, or I mean a graph of the 3 different map patches that I did. So as you can see, it's kind of small, but the differences aren't that large, but they are still distinguishable. The differences aren't that large because the map that we used is has a lot of noise, and also it's not as varying as some CMB maps can be. Like as you can see, this is still zoomed in, but it's not a lot of variance going on there. And we also one thing I want to point out is how the theoretical goes down and then ours goes up. So we have like this downwards. This is due to the 1/f noise or peak noise, and then this.
Can you talk near the podium for the people on Zoom?
And this taper noise is also like where it tapers off. That has to do with the white noise, and so ideally there would be no noise, which is why the theoretical goes down to that. I also didn't mention what the axes are. This L represents like the area of the sky, and L of 0 is the entire sky. And on the y-axis we have the mean power spectrum. Okay, so here are my results. I did 3 patches, but I could not fit them all in one slide, and I wish that I had a different map because most of the patches that I took, they all are very similar. But you can kind of see the differences in the point source mask. And I showed their individual spectra there. Now that is where you can see a bigger difference. One thing I also want to mention about the results is that we wanted to use unreleased ACT data, and that was it's a larger map with more differences in temperature, but this was a struggle in itself to get it to work, just due to some packages that we used that weren't functioning properly. And the size of the data was a really, really large challenge. So even this, I created an auto power spectra, but I wanted to create a noise power spectra, but could not do so with the code. It just simply would crash. So we are correlating the map with itself instead of using 2 different maps. Okay, so here I have a larger version of the all 3. And yeah, the maps are very, very similar. And that is the end of my presentation. So thank you guys.
Are there questions for Kaylah? Yeah, Morgan?
So you were saying that you had decided to not use the unreleased, I believe you mean the DR5 notebooks yet. Is that something you plan to do in the future?
It depends on, I guess, if I have the opportunity to keep working with the group. I honestly don't know how we would work around some of the challenges. I would need a better computer, or my mentor mentioned something, I forget what it's called, but another way to work with large data. But that really is the biggest problem, is that the data is too large. My code right now takes about 5 minutes to run each iteration, and it's only a bit over 200 lines of code. So that's very unfortunate.
Eric, you got a question?
Yes. One of the questions I had is there's in the power spectrum, yeah, the last plot, there's difference between the theory and the one you made. What could be causing like this difference? Is it because your data had a lot of noise, or?
Yeah, so this is a very noisy map, which is why we can call it essentially close to being a noise power spectrum, is because the map essentially has more noise than astronomical signal.
Carlton, did you have a question?
Very briefly, do you think you could explain again the difference between pink noise and white noise?
They are similar to each other. In our case, though, the pink noise is primarily due to atmospheric noise, and it is correlated, but the white noise is uncorrelated. So that's the main difference between the two.
Okay, we can do one more question, and then
Yeah, would you mind going back to the graph? Because I'm trying to understand the x-axis, and you said L of 0 would be the like entire sky, but like what happens as you progress to like 7,000? Like what does that mean?
So we're looking at smaller and smaller patches of sky, which means that we are looking at larger features in the map, right? Like the features are, how would you say, what do you call it? Amplified, you could say. So as you go along, although there's like, theoretically, as you go along, it would just be like zooming in and zooming in until you're not seeing anything.